Right. So it's time. If it's okay, we can start. Welcome everybody. It's my pleasure to welcome Ira Rothstein from Carnegie Mellon University, who will be giving a lecture on effective field theory for gravitational waves. Please.
Thank you. It's very nice to be here. I look forward to interacting with many of you as much as we can, given the situation. So hopefully you've been made aware of the fact that there are, there are lecture notes available, and hopefully, as I mentioned or as I noted on the front of them, you should be careful because there could still be typos in there, and I apologize for that. But I would appreciate if you do find typos that please send me an email, and in general, feel free to email me in between classes if you have questions that I'd be happy to answer in between classes. And I hope that you'll consult those notes for time's sake. I'm going to have to skip some steps calculationally, but most of the details of all the calculations of many of the things that I'll be talking about in class are in the notes. So for the steps that I skip during lectures, please consult the notes. And also there are exercises in the notes that I would recommend doing if you have time. And we can maybe in the question and answer section on the following day. I realize today it's too late, but I think on my next lecture on Wednesday, if you've tried any of the problems and you want to go over them, we could go over them in the discussion section. Also, I should warn you, so I'm lecturing in the morning, and so about this time is when my children go to school, and so you will probably hear noises, and I apologize. It will only last for 10 or 15 minutes before they leave. So
on the school bus.
Okay, so I apologize for that ahead of time. Okay, so hopefully everyone can see my iPad. My iPad is visible, right? Okay, great.
Yes.
Great. So we're going to talk about gravitational waves from the point of view of an effective field theorist or someone who has a training in particle physics. So I'll have to teach you both about gravitational waves. Valerie will be teaching the same subject from a more canonical point of view. So this will be complementary to her lectures. But I'll be also teaching you effective field theory at the same time. So I'm trying to teach sort of two subjects at the same time, and I've only got 4 lectures. So I'll do my best. At some points, I will have to ask you to just take things for granted and then consult the notes, because there simply won't be enough time for me to teach you both effective field theory and gravitational waves. So I'm going to assume minimal amount of knowledge of GR. So just if you know, I'm assuming you know what a metric is, and I'm assuming you know Einstein's equations and so forth, but nothing at the level of differential geometry or any of the technical issues that are often dealt with in GR. And I'm assuming that you've had a basic class in quantum field theory. But I think my lectures will be self-contained to that extent. So hopefully you'll have seen or be familiar with most of the concepts or technical tools that we'll be using in these lectures. Okay. And also, please feel free to ask questions during the lectures. And if it's technical and would take a lot of time, we'll wait till the discussion session. But hopefully, and if it's not, for just needs clarification, please please interrupt. Okay. So so before we go into this, I would just want to say a little bit about why this is interesting. So, if we're going to learn all this technical machinery and do these calculations, we should have at least some motivation for putting in the hard work. Okay, so so gravitational wave physics, why is it interesting to, say, a particle physics or someone who's interested in fundamental physics? So let me just give you a few of the reasons why I personally am interested. In particular, I believe that in terms of fundamental physics, the great potential is for new sources or new astrophysical objects, something like, say, a Bose star or axion halos surrounding binary systems. I mean, I think the fact that we still don't know what the dark matter is gives us hope that we will find signals that we have not thought of in the past, or something beyond the standard model. That is my personal opinion as to our best hope for finding new physics in gravitational waves. The other possibility, of course, is that we find deviations from GR. I personally think that that's probably highly unlikely, given the fact that GR is a very delicate theory in the sense that if you mess with it, it starts to fall apart very quickly. There are theories of massive gravity, but they all suffer some sort of, I don't want to say pathology, but they're very difficult to make work and be consistent with all known tests of general relativity. Finally, from a fundamental physics point of view, the question of the neutron star equation of state is still an open question. So is the neutron star in a hadronic phase, or is it in a quark phase, quark-gluon plasma? These are unknown questions that in principle we will be able to address or learn about from gravitational waves in the future. And we'll talk a little bit about how one could go about trying to learn something about the nature of the equation of state of neutron stars. So this is really a question of QCD and is related to heavy ion collisions and so forth. So from a particle physics point of view, that's really an interesting question. Now, there's also the issue of what can we learn about black holes. Now, it's very unlikely, very unlikely, that we'll be able to learn anything about, say, Hawking radiation or the information problem from gravitational wave physics. And if we have time in the last lecture, we'll talk a little bit about maybe about how Hawking radiation, why Hawking radiation is so negligible, even though at first mathematically it may seem to the contrary. And there are a remarkable number of claims in the literature that that Hawking radiation could have an effect on a signal, but I'll explain to you why I think those claims are false. But one really interesting aspect about black holes, which I hope we get to by the final lecture, is that they they have a very unique property in the sense that a classical property that hasn't been tested before, and in the sense that they have vanishing polarizability. This is a prediction of GR. Which is to say that if you put a black hole in a background field, it will not generate a quadrupole moment. So think about the analog of an electromagnetic case. If you have an atom and I put it in an electric field, it generates, say if I put it in a constant electric field in this direction, it will generate a dipole moment in that direction. For black holes, if you put it in a background field, then it will not generate any multipole moments. This is a really strange result, which is, which is a prediction of GR, and we will be able to test that in gravitational wave experiments. From a point of view of a particle physicist, this again is rather enticing because it leads credence to the idea that black holes are fundamental objects. In a sense, if I had a point particle, if I put it in a background field, it doesn't distort because it has no size, right? So if we think about black holes as almost as fundamental objects, even though they have finite size, then that's consistent with that interpretation. It's a rather remarkable prediction of general relativity. So those are the fundamental, from the point of view of fundamental physics, why gravitational waves are interesting. Astrophysically, of course, has its own motivations for studying gravitational waves. So in particular, there's a question of black hole formation. How do black holes form? Okay, so as you all know, what we're looking for in a gravitational wave experiment are in-spiraling binaries, right? So you've got compact objects that they're caught in an orbit, and they radiate. As they radiate, they in-spiral, and they form this famous chirp signal that probably you're all familiar with by now. But we don't really know how those binaries form. So there are various mechanisms for how two black holes can capture each other. So actually, so the three known mechanisms. One is the so-called in the field. And in this mechanism, you have two stars that are in a binary. One of the stars during its lifetime grows to be a giant and envelops the other one. They have a cloud that surrounds them. Then eventually they both go supernova. They explode, and you end up with two black holes after it ejects off all the material. And these black holes typically are predicted to nearly have the same mass. And the spins are aligned. The spins are aligned with the orbital plane. Okay. Then there are dynamical binaries, and these are binaries. So typically these in the fields are born in low density regions. And a dynamical binary is born in a high density region, usually in what's known as a globular cluster. And when you have a very high density region, it's just there's some finite probability the two guys will will be in dynamical range of each other, and they'll just get captured. And in this case, there's the masses are not expected to be necessarily the same order. The spins are random. Randomly aligned. And so in principle, if we could measure the spins and the masses, then that would give us some clue as to whether or not it was a dynamical binary or an in-field binary. And then finally, there's primordial black holes, which could have fallen under the category of fundamental physics. And these are black holes that were formed in the early universe, prior to, say, star formation even, where they were due to fluctuations in, say, the inflaton field, whatever caused structure to be formed in the early universe. And this is, of course, more speculative. We have some ideas of how they formed, and it's sort of sensitive to the power distribution and the nature of your inflationary model. So this is more speculative. However, by making these measurements, we can distinguish between how many black holes we expect are from in-field binaries versus dynamical binaries. And so you can make a prediction for the black hole population and the mass distribution. And there's a prediction, I'm not going to go through the details, that there should be a mass gap. So there should be a region between 50 and 150 solar masses where there are no black holes. This is called the mass gap. This is what the standard predictions are for the black hole populations. And already we know that, in fact, that this is not true. So that mass gap has been populated. There are events in there. And so we've already learned something. Perhaps new physics is probably too strong of a word in the sense of a particle physicist. It's nothing beyond the standard model, but there seems to be some tension with the theory of black hole formation and the data at present. So already, even though LIGO's only really been running for a few years, we're already learning new things about black holes that we hadn't expected. So as the number of events grows and the number of detectors grow, I think I would be surprised if there weren't many more surprises in store for us. And hopefully we'll see signals that don't fit any of our predictions whatsoever, right? So our job as theorists is to make predictions for some sources that we imagine. But if we want to distinguish between a black hole, say, and a magnetar and a Bose star or an axion source or any dark matter sources that may be compact and go through in spirals, then we have to know what the background is, right? So much like at the LHC, if we want to look for supersymmetry, we need to be able to eliminate the background. So from a particle, from the point of view of a particle physicist, thinking about gravitational waves, just as we would make a prediction for the LHC, if you're going to build a SUSY model or Technicolor model, whatever your favorite model is, that goes beyond the standard model, before you tell the experiments what to look for, you have to tell them what the background is, okay? So whether you're interested, say, in gravitational waves because you're looking for new physics, or if you're interested in gravitational waves because you're interested in astrophysics, in either case, we need to be able to make precise predictions for the gravitational wave signal. So my lectures, what we're gonna do is discuss how we use effective field theory techniques to make very precise predictions for gravitational wave signals. Along the way, of course, we'll have to learn about effective field theory a little bit in order to be able to develop the proper formalism. So let me pause for a second and see if there are any questions.
Yes, there is one from Anna, please.
Professor, I just wanted to ask if you could please tell us a little bit more about the theoretical origins of the mass gap claim, because I've seen that, LIGO sort of disproved the mass gap claim, but I'm not really sure where the claim came from in the first place.
Right. So I can say a few things about it. I don't want to get too far afield for two reasons. First of all, it's not my area of expertise. But second of all, it could take a little bit of time. But basically, if I remember correctly, so if you have let's take certain limits, okay? So so for instance, how large of a black, the progenitor, the mass of the progenitor will determine the size of the black hole, essentially. So without going into details, depending on the size of the progenitor, you may blow off a different amount of stuff when it goes supernova, right? So in order to predict the mass of the remnant, you have to have some theory about how much stuff gets blown off. So if you're too massive, what happens is basically everything gets blown off, and all you're left off is the core. So if you knew the mass of the core, then you would know the mass of the whole. But if you have intermediate masses, then different amounts of stuff could get blown off. And so there's some region where there's some region of the progenitor masses where whatever's left over will never fit in that mass gap. Now, to be completely honest, how they get the exact numbers for the mass gap, I think they have some models. So, I mean, is it a huge surprise that the mass gap is actually populated? I mean, personally, as a non-expert in the field, I would say probably not, is because in the old days, in fact, the computer simulations couldn't even get the supernovas to blow up. I don't know what the status is now, but when not too long ago, there was the computer simulations of supernova explosions were really struggling to even to catch on fire, right? So it doesn't, as an outsider and non-expert in those calculations, those are extremely difficult calculations to do. So to calculate the mass of the remnant is really hard. But in short, the answer to your question is that for different ranges of initial progenitors, the mechanisms for collapse can be different, right? So there are certain ranges where you just can't fill the gap where those between 50 and 150 solar masses. Yeah. So as I said, I'm far from an expert on that subject. So I'm afraid I can't give you a better answer than that.
There's another question by Anirudh.
Hi.
Hi.
Regarding this mass gap, as far as I know, like you can have some inflationary models in which you can still produce these black holes from 50 to 150 solar masses during the radiation dominated era. So is it different? Because I don't see, I mean, at least from what the consensus is right now, like there should be no problem to have an inflationary model which produces these black holes in this mass gap.
Yeah. So the mass gap is a prediction. The only source of black holes are stellar.
Okay. Okay.
Yeah.
Mm-hmm.
Okay, so let's talk about how particle physicists goes about thinking about predictions for gravitational waves. So we have to talk. First thing we should discuss are what are the observables. Okay. Now, if we think about collider physics, what are the observables in collider physics? Okay, so in collider physics, of course, we have some scattering, we have some in, and we have out, and we calculate cross sections, right? And these are proportional to some matrix elements squared, right? And so we measure we have our detectors. We consider our detectors like being at infinity, and we calculate some transition rates. So how do we apply the ideas of particle physics to gravitational waves? Well, if we think about gravitational waves, what are the observables? Well, you've got some sources. Here's some inspiraling binary, and here's our detector at infinity. And all we see is a wave. So basically, there are two observables. One is the amplitude, and one is the phase. As compared to, say, a collider where you can make up an infinite number of observables, right? You have inclusive cross sections, exclusive cross sections, weighted cross sections. Whereas here, things look much simpler, right? All we have is an amplitude and a phase. Now, of course, a crucial distinction in the sense of how much information is in the signal lies in this time dependence, right? So if you if you consider the time evolution of the system, you know, as time goes on, the system starts to shrink. And the velocity increases. So this is V1, V2, V3. Okay, so there's a lot of information in the time dependence of the signal. You know, probably, you know, you've all seen this. If you look at it as a function of frequency, so if you look at the peak frequency as a function of time, it looks something like this, right? And you hear that whoop that's called the chirp, which comes at the end here. Okay, so our goal will be, given some initial conditions and some set of parameters, what we'd like to be able to do is to make a prediction for A of t and phi of t. Okay, seems simple enough, but why is it quite to the contrary? So let's think about this, all the physical effects that are going on here. So we've got some matter distribution. Let's call this 1, and we'll call this 2. And they're trapped. So there's some, from the point of view of particle physics, we would call this, there's some exchange of gravitons here. We'll call this, that generate a potential, okay? And that potential is the binding due to gravity. And these guys are caught into an orbit. And what happens? What's the dynamics responsible for the infall? Well, there's a huge amount of physics going on here. So these guys, of course, will radiate as they accelerate. And as they radiate, they'll lose energy. And then that, in course, increases the velocity as they start as the orbit starts to shrink. But there's a lot more to it than that. In particular, will deform each other, right? There'll be a tidal force which will elongate them. And this tidal force changes their shape. The shape will then change, the potential will be new due to the change in the shape, right? Which in turn will change the rate at which the in-spiral occurs. On top of that, because gravity is a nonlinear theory, really interesting things start to happen. So you can imagine this guy emits a graviton. That graviton scatters off the gravitational background of this guy and comes back and hits itself. That will change the motion, right? Or you could have this guy radiated graviton, this guy radiated graviton, scatters and come back and hits itself. That will change the motion. This is an incredibly complex problem. And to calculate the phase and amplitude is extremely complicated and difficult. So in order to calculate the radiation, we've got to sort of solve all these problems together at the same time. Now, of course, is one in some sense most straightforward, and I use that term in a remarkably glib and insensitive way to those who work on this incredibly hard subject. That is numerical relativity. Okay, so you just plug it into a computer and calculate. So indeed, there's a whole field of numerical relativity, and numerical relativity, in principle, is the solution to this problem. In practice, it's extremely computationally expensive. In that running a simulation takes months, and the way the experiment works is they use what's known as a template bank. So I'm not going to go into details about this, but I think it's important to understand. So basically what they do is, how do they search for a signal? They use something called match filtering. Basically what that is you have your prediction, and then you take your signal and then you convolve them, you integrate the product of the two, and you see how well they overlap, okay? So, but in order to do that, you have to remember that the signal, let's call it S, will be a function of M1, M2, S1, S2, as well as other parameters which I'll discuss. But basically every binary is characterized by the masses and the spins. There's also some other parameters here which we will discuss, which are finite size effects, which to me are the most interesting effects. So these include things like the polarizability, these are sometimes called the love numbers, which we'll discuss. So for instance, these love numbers would distinguish, say, a black hole from a dark matter star, or whatever exotic object you're hoping to find in the signal. And so the way they build a template bank basically is for every value of M1, M2, S1, S2, they have to have a signal, right? They have to have a prediction. So what they do is they have a bank of these predictions for all these masses, and obviously there's a continuum number of these, and you can't possibly hope to build a bank numerically. It's impractical, right? Because as I said, each simulation takes months. So to build the banks, they actually use a combination of analytic results, which is what we'll be discussing, and they put them into some models. So it's not quite completely systematic from the point of view of the errors are 100% under control. But the part where the errors are under control, the parts we'll be talking about, right? So as particle physicists, we've been spoiled to always calculate in a systematic way, where you can make a prediction and then tell the experimentalists, this is our prediction and this is how big the errors are. And as a theorist, if you make a prediction without bounding the errors in some way, then you can't claim to make a discovery, right? So any prediction at the LHC, when they say there's a 5 sigma, which is the criteria for discovery, a 5 sigma signal, that includes some sigma from theory, right? Without a sigma from theory, then that discovery is of questionable worth, right? So now, which isn't to say that every prediction at the LHC is completely under systematic control itself. So it would be disingenuous to say that we as particle physicists have some sort of higher standard, because there's always modeling of hadronization and fragmentation. We believe we understand those things, but it's often just based upon a model. So I'm going to distinguish between a model and a first principle prediction. That a first principle prediction must have an expansion parameter that bounds the errors. Okay. So so we will be discussing analytic methods based on first principles with well-bounded errors in the context of effective field theory. Okay. So so we have to have an expansion parameter in order to make a systematic prediction. Is my see my screen again? I know it went off. Yeah. Okay.
Yes. Yes.
Okay. So we need an expansion parameter. So our expansion, what is we have to have something, some small dimensionless quantity. So I'm going to use particle physics units. Okay. And a natural expansion parameter arises always in some limits, right? You want to take some limit where you have total control of the situation. So one such limit is when the velocity is much, much less than 1. So I'm going to drop C from now on, but that's the limit we're going to be interested. That's going to be our expansion parameter. And essentially, in GR, this is the only expansion parameter under which we have systematic control. This is sometimes called the post-Newtonian approximation. And basically, it's an approximation when V is much, much less than 1, the curvature is small. That is, it's nearly flat space. So the way to see that this is nearly flat space So if we look at the metric of a spherically symmetric object, right? So the metric is the Schwarzschild metric. Oh, and I'm also going to be working in plus, minus, minus, minus. So this is what the Schwarzschild metric looks like. The angular piece. It's an omega, sorry. So if we have a binary, then the centripetal force should balance the or the centripetal force needed to keep the system intact should be equal to the Newtonian force, the gravitational force. And so this tells us that sorry. Okay, so v squared so if we were to set this to 0, we'd be back at flat space. And you can see that as v goes to 0, we approach flat space. Okay, so the reason we can get calculational control in the small velocity limit is because we're approaching flat space where we know how to calculate everything. Okay. Good. So that's our expansion parameter. And the next step in approaching this problem, in trying to parse this problem and to simplify it, is to understand, let's understand all the scales involved. So what are the relevant scales? Okay, so let's see what's going on here. So here are our objects. So let's assume that the objects have the size of order the same size, which is typically true for almost all the cases we'll be interested in. So we'll call that big R. We'll call the orbital separation little r. And we're going to make the assumption that R is much, much greater than R. And that's a reasonable assumption to make if we're interested in the small velocity limit, right? So they'll be moving slowly when they're far apart. As they radiate, they'll start the orbital distance will get smaller. They'll speed up. So this hierarchy is consistent with our small velocity approximation. Now we have one other scale in the problem, which is the wavelength of the radiation. So the wavelength of the radiation goes like 1 over omega, which goes like R over V. Okay, so we have another scale in the problem when V goes to 0. So those are the 3 scales in the problem. What we would like to do is to simplify this problem by treating one scale at a time. So the essence of effective field theory is divide and conquer. Okay, treat one scale at a time, because when you treat one scale at a time, all the calculations simplify. Okay, look, what we're really doing, what our job is to solve Einstein's equations, but we will never even write down Einstein's equations. Okay, we're going to solve the problem by using methods of quantum field theory, despite the fact this is a completely classical problem. So even if you're not interested in gravitational waves per se, the methodology we'll be discussing will be applicable to many other systems. And in fact, the methodology that we developed was based on ideas used to study heavy quark bound states. So the physics of heavy quark bound states is remarkably similar to the physics of an inspiraling binary, right? So when you have a heavy quark bound state, the typical radius is very small compared to the QCD scale, so it's weakly coupled. So those of you who are familiar with QCD know that QCD is asymptotically free, which means at short distances it's weakly coupled. So a bound state of heavy quarks is a weakly coupled bound state in a nonlinear theory. But what is gravity? It's a nonlinear theory, and at small v, it's a weakly coupled bound state. Now, the huge distinction, of course, is that quantum effects are order 1 in quarkonium, and quantum effects here will be suppressed by h bar over the orbital angular momentum of a binary system. So you can imagine how small quantum effects are. So you can do a little back of the envelope calculation and take h bar and divide it by the typical angular momentum for, say, solar mass black holes, and you'll see that's a pretty small number. Okay, so I think we're 48 minutes in. So why don't we take a little break and get up and stretch a little bit and come back in 5 minutes?
Great. So we'll resume at 54, right?
Yep.
Okay, great. Thanks. Here we are. There may be questions. I don't see any. All right. Whenever you want.
Okay. Good. So how do we attack this problem? So as usual, you first start with a simpler problem and build up your intuition and your technical chops on that problem before you attack the harder problem. So the natural analog or the toy model of this problem would be electrodynamics. Okay, so first we're going to look at electrodynamics. And this problem is considerably simpler because the theory is linear in the sense that the photon doesn't interact with itself like the graviton does. So it's a much simpler problem to solve, but to be completely honest, it's also intractable, right? For the same reasons that we discussed before. You know, even if I have a system of charges that are interacting with each other, and I want to calculate the radiation, that problem in itself is not solvable in closed form, obviously, for the same reasons we talked about before. These guys deform, and as they in-spiral, the deformation changes, and as they deform, the forces change, and as the forces change, the radiation changes, and the radiation leads to new forces, some so-called radiation reaction forces, which hopefully we'll have time to discuss. And so this problem is again unsolvable, but we again can attack it in the small velocity limit. So let's talk about how we would solve this problem. Okay, so basically, if we think about it from the point of view of a field theorist, right? We have some partition function over the fields. Okay, where phi now is a generic set of fields. Okay, now the idea in effective field theory is to break up the system into different sets of fields which live at different scales. Okay, so we mentioned before what the scales are. We have this hierarchy. So we're going to break the field up into phi. Let's call it phi r, and phi r over v. Okay. So this set of fields only have, this field only has momenta of order 1 over r. This guy only has momenta 1 over r, and this guy has momenta 1 over v over r. Okay, that's incredibly imprecise at this moment, and we'll have to sharpen that slightly. But for the moment, just so we can get a little bit of intuition, so then we can write our path integral. In this way. Okay. Now the idea is, well, at long distances, what's happening at short distances starts to become irrelevant, right? In a very precise way. So we do things in steps. First, we do the path integral over the shortest distance modes. And then we end up with a new effective action. Okay, so this new action will encompass all the physics of the short distance modes here. Okay, and then the next stage, okay, and this is what we're really interested in. So as an observer at infinity, the only fields we see are these. Okay, so this procedure is sometimes called integrating out. So we integrate out the short distance modes. So these are the shortest distance modes. These are the next shortest distance modes. As an observer at infinity, all we care about are the radiation modes, which are the longest distance modes. So if we knew this as effective, we could calculate everything we wanted, the phase and the amplitude. And then we'll have solved the problem. Of course, we can't do these integrals exactly. We can only do them in some approximation. But as long as it's systematic, we can still have a prediction which is meaningful. Okay, so what are these modes? So let me just tell you the answer, and then we'll spend the rest of today and maybe part of tomorrow, depending on how much time we have, justifying it. So there are basically the three types of modes in this problem. The phi r modes are the modes responsible for the internal dynamics of the object. Okay, so if this were a neutron star, it would be the normal modes of the neutron star, or whatever the object is. In the case of a black hole, they're called quasi-normal modes. They're the ringing modes of a black hole. If you strike it, it will ring. And really, to me, this is the most interesting piece of physics, because it's the short distance physics that distinguishes between normal matter and, say, dark matter. But of course, we don't have direct access to those modes. We only have indirect access through how those modes affect this action. Okay. Now, all of you actually know how to do this first path integral. Okay, let's look at the electrodynamics case. If I have a collection of charges and I ask what is the potential at some point r, we know, at least if they're static, okay? So that is what the potential would be at some distance. Now we know that if this guy has some region of support r, and we're looking at a distance r, and r is much greater than r, then we can expand this integral, and we end up with q times 1 over r plus p dot e times r cubed plus dot 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 dot. Okay, this is called the multiple expansion. Okay, you're all familiar with that. And this is the simplest example of an effective field theory. It's a completely trivial example of effective field theory. Nonetheless, it captures a lot of the ideas. So notice that all the short distance physics is encapsulated in these coefficients. So Q if I knew rho of r exactly, Q would be this, and P would be given in this way. And in the language of quantum field theory, we will call these, so these are short distance coefficients. And they're also sometimes called Wilson coefficients. Okay, and so to think about this more clearly, we could label short distance objects by red and long distance objects by green. Okay, so the short distance physics, it would be incorrect to say the short distance physics is irrelevant for the long distance physics. The more precise statement is that the short distance physics is encapsulated by a finite number of coefficients, which are just pure numbers. Okay, so we can describe this long distance physics, the fields at infinity, by a finite set of numbers, Q, P, and then I can have a magnetic dipole moment, and then I would have a quadrupole moment, Qij, octopole, so forth and so on. And so these are just a collection of UV coefficients. UV meaning short distance. Okay, so if I don't know what this distribution of particles is, like in the case, these particles would be the analogs of whatever the degrees of freedom are that make up the objects that are in spiraling. So we don't know what they are. We're trying to figure out what they are. These are a set of unknown coefficients, and we're going to use the data to measure them. So that's exactly what we're doing in a gravitational wave experiment. Okay. So for the sake of simplicity, let's assume that our system is spherically symmetric, right? So we're going to assume that our in-spiraling objects have the shapes of spheres. If they didn't, we would know what to do. We would have to include multiple moments for them. So we're going to assume spherical symmetry. And of course, for astrophysical objects, that's an excellent approximation, if they're not spinning at least. So non-spinning black holes are described by the Schwarzschild solution, which is a spherically symmetric solution to Einstein's equations. Okay. So once we do the multipole expansion, then this leads to the point part is basically a point particle description. Okay, so the first step in our approach is to reduce this to a point particle and reduce this to a point particle. Okay, now we have to make sure we capture all the finite size physics, because that's what we're interested in when we're done, right? We're interested in knowing, you know, how did this thing deform? How did it, you know, all the stuff that is, all the physics that's captured in the internal dynamics of the object. So what we want to do is we want to figure out what is S effective. What is the effective action for point particles? Okay. And the logic behind this, the process of determining S effective is we write down an action which is consistent with all the symmetries, right? So first of all, you have to figure out what the symmetries are. But before we do that, you know, we started off with an action for a bunch of point particles, and now we have an action for 1 point or 2 point particles, and we have to describe the position of those 2 point particles. So we're going to describe them by world lines. So I is equal to 1 or 2. Lambda is some affine parameter. affine parameter, meaning it's just a parameter that has no preferred origin. So there's no such notion of lambda equals 0 being some preferred point. So this is our x mu of lambda, and I've left things relativistic here. So x0 is a time coordinate, which may or may not be the same as lambda, which we'll see in a second. So here's our x mu I of tau. Here's x1. Here's x2. We'll give it a different parameter, lambda prime. And now we want to write down a Lagrangian, which is a function of xi, say, and perhaps xi dot. For these point particles, right? So this is going to be our effective action. So we can write S as, so let's write it as a sum over I1 and 2. Mi, so this is the kinetic term for a relativistic point particle. So eta mu nu for the rest of these lectures is the flat metric. Okay, I'm not going to derive this for you. Hopefully it's familiar to you. There are lots of different ways of deriving this, but for the moment, let's just take this for granted. It may be during the discussion section, if there are questions about where that comes from, we can discuss. I prefer, in general, not to just ask you to accept a result, but for the sake of time for the moment, let's, in this case, just assume that that's true. And now we need to couple the point particle to the electromagnetic field, right? So A mu of x is going to be our gauge potential. And now we want to couple it in a way which is consistent with all the symmetries. So what are the symmetries? That's the first step in writing down any effective theory. You have to know what the symmetries are. Okay. So certainly in QED, we know that it better be gauge invariant. And if we're writing down a point particle description, it had better be independent of how I parameterize the world line, right? I can parameterize the world line in any way I wish, and the physics shouldn't change, right? I could, if I have some parameterization x mu of lambda, I should be able to parameterize it by lambda prime, where lambda prime is some function of lambda, and leave the action invariant. This is called reparameterization invariance. Okay. So what can I write down? Okay. So the first term I can write down, in addition to this kinetic piece here, is I can write down d lambda of v mu of lambda x mu. Okay. And I'm going to put the charge in front of it. And I'm going to sum over I. So let's see if this is invariant. Well, under a gauge transformation, our first symmetry, so delta S will look like d lambda dx mu d lambda d chi dx mu. Sorry if my lambdas look like chi's. And this thing is a total derivative, so I can just set it to 0. It has no effect on the physics. So this is indeed, at least from gauge invariance, we found that it's invariant under gauge invariance. Is it invariant under reparameterization invariance? Well, d lambda goes to d lambda prime, sorry, d lambda over d lambda prime. But V that should not be a partial, sorry. And this is, so if we look at this action, the variation of this guy exactly cancels the variation of V. And indeed, that is an allowed term in the action, okay? Now, of course, we also have to include the action for the electromagnetic field, which does not live on the world line. This is just QED. So we're going to call this the notation. I should really write this in red. This is a short distance coefficient. And corresponds to the total charge of the ith blob, right? Okay. Now, from the point of view of effective field theory, I have to write down every possible term. So, of course, there are an infinite number of terms that I could write down. So let's start to write down the next order, higher order polynomials in the fields. Okay, that are consistent with gauge invariance and reparameterization invariance, okay, that live on the world line. Okay, so finite size effect, these will account for the finite size effects. Okay, so let's write down S finite size. Well, we have our integral over our affine parameter for each guy. And now let's write down everything we can, which is gauge invariant. Well, I can write down on the world line, F mu nu, F mu nu. That is still, of course, gauge invariant. And I have to include some short distance parameter, let's call it C1, into the action. This is unknown, but in principle calculable if you know what the underlying system is. Okay. Now, I can write down also at quadratic order in the fields. I can write down another term with another short distance parameter. Okay, which is gauge invariant. I should say, I realized I glossed over something, which is that we're also assuming Lorentz invariance. Sorry, apologize for that. Hopefully that was obvious to you guys in the sense that we want to write down Lorentz invariant theory. Eventually we'll break Lorentz invariance because we're going to take a non-relativistic limit. But for the moment, we haven't made any approximations about small velocities. Everything now still is completely relativistic, okay? Now, we're not quite done because this system, we haven't imposed reparameterization invariance, but I can fix that by putting in a square root of V squared here and a 1 over the square root of V squared there. So you can check for yourself V transforms in the opposite way as lambda. So these guys, they cancel each other. And I've got two V's upstairs, so I've got to put a V down here. And that leads to the Jacobian, the transformation canceling. Okay, so there are, of course, infinite number of terms that one could write down, but we've truncated, so we have to be truncating in some expansion. So let's do a little bit of dimensional analysis. These operators have, these coefficients, just on dimensional grounds, scale as r cubed. Okay, so you can see that by just counting derivatives and dimensions of the fields. If there are questions about this, we can go through a detailed example in the discussion. And so R, remember, is the parameter which we're taking to be small. So as long as we're studying scales R, little r, much greater than big R, then terms which, next order terms, which say will scale like r to the fourth and then r to the fifth, lead to our small corrections, which in principle could be included. So as an exercise, you could start to write down the next set of polynomials, the next set of operators at higher order in the fields. So so far, when we're doing the point particle approximation, we're doing expansion in big R over little r. And we've essentially accomplished our first stage of the effective field theory. We've removed all the short distance physics. The short distance physics is completely encapsulated in our red Wilson coefficients. Okay. Okay, so let me pause for questions.
Any questions?
Okay. Well, if there are no questions, so what's the next stage? Well, the next stage is removing the next set of degrees of freedom. And in order to do that, we have to know what they are. So what are the next set short distance, next collection of short distance degrees of freedom? Okay. Now, that first step was the easy step, right? That's the multiple expansion is something you learned in undergraduate physics. The next step is more difficult. So to give you the answer before proving it, there'll be modes which are responsible for the binding. Those are called potential modes. And then there's the radiation modes. The potential modes will have typical wavelength of 1 over r, and the potential modes will have typical wavelength of v over r. Okay, so the next step of modes will be short distance modes will be the potential modes. So we're going to want to integrate out those guys. These are just words. So let's show that this is true. And the way we'll show this is true is by using the path integral formalism and understanding the details of the problem. So let's consider the path integral of the partition function for some system where electromagnetic system where X will be the sources. So these are charge source. Notice that I've assumed that the action only depends on X and X dot. And the reason for that is that if you had an X double dot, you could always use the equations of motion to replace X double dot by X and X dot. Now, the obvious question there is, well, equations of motion are classical. And if I'm working the partition function, what gives me the right to use the classical equations of motion? Because the quantum fluctuations don't obey classical equations of motion. We can talk about that. For us, of course, it's not important because we're doing a classical problem. So we're certainly allowed to do that. We don't need to worry about quantum fluctuations. If people are interested, we can have a discussion about why even quantum mechanically that's an allowed manipulation. Okay, so quantum mechanically, even though we're doing a classical problem, the partition function we know is known as the vacuum persistence amplitude. Okay, so this is the probability to go from minus infinity in the vacuum to plus infinity at the vacuum in the presence of these sources, of these charges. And this is just normalized to the transition probability without the sources. Okay, so in our case, in terms of the path integral, we can write this. Okay. So it's a vacuum transition amplitude in the presence of the sources. Okay, so what can we learn from this? Well, if we look at this object, then we know how the vacuum will evolve in time. It's just e to the iht acting on the vacuum. So we can write z as just a phase. Times t, and this is where t goes to infinity. Okay, times some overall normalization coming from the denominator, right? So if you're in the vacuum and you're asking what's the probability be in the vacuum at time equal infinity, the system evolves. We're assuming some notion of adiabaticity. So you've got some energy at the ground state, and as the system evolves, it accumulates a phase. When that phase, oh, sorry, there's an integral here, sorry, because there's time dependence. And it just develops a phase over time that's given by just the energy. Now, of course, if you're in the presence of sources, which are dynamical, they will radiate. And so we'll see in a second that this energy has an imaginary part, and that imaginary part will correspond to the rate at which things are radiating. The real part will correspond to the potentials, and the imaginary part will correspond to the radiation. Okay, so let's see if we can calculate this object in electrodynamics. And in fact, the reason we're doing E&M is because we can solve this problem, right? E&M is Gaussian. So we can do this exactly without even making the multiple expansion, or we can do it for arbitrary sources. So remember, what is the action for QED? So here, this is the gauge fixing term, and I'm going to always work in the Feynman gauge just to make our lives easier. So this integral, the path integral is doable. This is quadratic in the fields. It's Gaussian. So z of j okay. So notice here, I haven't made any approximations. This is exact. This is a general J, right? Eventually, we'll replace it by point particles. Okay. So now this guy, this object here is essentially I, times T. Okay. And what I claim is that the real part of this object will tell us something about the power loss in radiation. And the imaginary part will be the potentials, which gives us the forces between the objects. Okay, so since we're running out of time, let me just quickly say, so what we're going to do next is we're going to take J mu as point particles. So they will have the following form. This is J mu of x. And we're going to plug that into here. And from that, we're going to extract the power loss and the potentials. Okay, so that's the next order of business. We'll have to say a little bit about what this G is here. So for those, hopefully that's familiar to you from your field theory classes. So that's going to be a propagator, but we're going to have to figure out what are the correct boundary conditions on the propagator in order to get the physically physically correct solution. So I think I am out of time for today. So we can stop and have a discussion.
All right. Thank you very much. Thank you very much, Ira. And we have already a question from Max.